Okay, moving along. So let's get into heat transactions. So this is now where we're going to start getting into hopefully also some familiar ground, talking about calorimetry and heat capacity. Okay, so for now, this is another one of these scenarios, constant volume process. Okay, we can also talk about a constant pressure process. So this is kind of the game we play, simplifying our scenario, right? Defining what we're dealing with here. In this case, let's just talk about a process that's constant volume. Okay, so it can be shown quite simply that the internal energy of a constant volume process is just Q, because for a constant volume process, let me write this, let me write this for infinitesimally small changes. dW equals, du equals dW plus dQ. So for all constant volume processes, work will equal 0. If there's no change in volume, there's been no work done, okay? And so du will equal dq, or delta u will equal qv, all right? And something I want you to get used to in this class, the subscript that we put down there denotes that something's being held constant. So when I put a V, and I meant that for to be a capital V, okay, as volume is a state function, then that denotes that volume's constant. Okay, so again, let me write that down. When I write QV, that's heat at constant volume. The V indicates volume is constant. Okay? So we can study this process via calorimetry, the study of heat transfer. Okay? And so we can write QV as the following: CV times delta T, where CV is my constant volume heat capacity. I'm not writing constant volume down there because that little v down there tells me that it is constant volume. Okay? And then we recognize that delta T is the change in temperature, T final minus T initial. So this heat capacity, CV, has units of joules per Kelvin, and then temperature is Kelvin. So this just gives me units of joules, so that's the extensive parameter. So in other words, if I'm talking about the heat capacity of 1 gram versus 100 grams, that matters, right? 100 grams of material will be able to absorb more heat than 1 gram of material. But what about intensive? Okay, so for intensive, we use the specific heat, okay, which has units of joules per gram per degree Kelvin, or some of you are probably used to seeing that as joules per gram per degree C. It's the same thing, right? Because the change in temperature for 1 degree Kelvin is the same in temperature for 1 degree Celsius. And of course, this mass here would be the, I should have wrote lowercase m, apologies, but we'll just say mass of material in grams. So not the molar mass, just the mass in grams. And so, right, when I multiply all those units together, that also gives me joules. Okay? So you're probably far more used to seeing this intensive version of the equation, right, with specific heat, joule per gram per Kelvin, okay? But we also can have this extensive, just joule per Kelvin, right? And so with our specific heat, so what this all means, so I'll give you an example here. So we know water, I'm running out of room here. So we know H2O liquid is 4.184 joule per gram per Kelvin. And so what that means is, if I have 1 gram of liquid water and I want to raise its temperature by 1 degree Kelvin, I need to supply it with 4.184 joules. Okay? So if we look now, the definition of heat capacity, So by definition, heat capacity is the partial, and don't forget what partial derivatives are. Okay? Partial of U with respect to the partial of T at constant volume. Okay, at constant V. Okay? So what does this mean? Well, if I have a slope of U versus T, I get a relationship. And for now, I'm just going to kind of draw you a simplified relationship. It looks something like this. Okay? So the slope of this line is the heat capacity. Okay? Slope equals CV. All right? And there's something really cool that happens related. Let me draw this arrow a little bit more clear. Related to the equipartition theorem, there's something really interesting going on here. Okay? If we look at a really vast range of temperature, so perhaps like, 0 Kelvin to, I don't know, 10,000 Kelvin, right? Some giant range, okay? The relationship of internal energy with temperature is not going to be linear. So there's some kind of curvature going on here, okay? And we're going to get into that detail soon. But if I look at the range that I'll call, approximately room temperature, 298 K. And by approximately room temperature, that spans some region like A to B. Then the heat capacity, assuming I can draw this, oh yeah, that's good. Heat capacity will be somewhat constant. I should change the color of that so that's like really clear, okay? So over some range, thereabouts in room temperature, that slope of U versus T will be constant, okay? And for now, just think of it as, 298 plus or minus, I don't know, 50 or something, okay? I don't want to put a hard range on that yet, but we'll just say, at approximately room temperature, heat capacities are constant. So for example, this specific heat of water, right, that's the room temperature value for the specific heat of water. At a different temperature, that value is different. However, there is a nice range, a fairly large range, where U versus T has a constant relationship, and thus you can use a single value of heat capacity. Okay? So let's do another activity. Come up with expressions for the heat capacity for a representative monatomic gas, linear molecule, and nonlinear molecule. How does heat capacity of a nonlinear molecule compare to that of a monatomic gas? So it's the same activity I had you do before, but now you're coming up with heat capacity. So feel free to pause it if you need to. I'm just going to go for it, okay? And I'll remind you that CV equals the partial of U by the partial of T at constant V. So remember, a monatomic gas, UM as a function of T equals UM 0 plus 3/2 RT. So how do I use that in this relationship? Well, recall it with partials, okay, I can say now, okay, partial with respect to T, and I'm going to supply my equation for U, okay, which is UM, I'm going to start writing instead of UM as a function of 0, I'm just going to write UM 0 up top right there, okay, plus 3/2 RT. So, and then that's all that constant V, and I could put that little V down there being constant so I would know the V is being held constant if I wanted to. It's a little redundant. The mathematicians will tell us we don't have to do that, but chemists, we like to put the variable that's being held constant, okay? So this is a very easy derivative. This is a constant, so when you take the function of this with respect to temperature, it's 0. And the derivative of 3/2 RT is just simply 3/2 R is the heat capacity for all monoatomic gases. Not the specific heat, just the heat capacity, CV, okay? So what about a linear molecule? Well, we remember linear molecule, I'm just going to simply write this, was 5/2 RT, and nonlinear molecule was 3 RT, right? So now CV for a linear molecule is going to be ddt of 5/2 RT, which is just 5/2 R. Okay. What about the nonlinear molecule? ddt of 3 RT is just simply 3R for a non-linear molecule. Okay, how does the heat capacity of a nonlinear molecule compare to that of a monatomic gas? 2 times. It's 2 times the difference. And what does that mean? That means to get the same rise in temperature, a nonlinear molecule has to be supplied twice the amount of energy as a monatomic gas. So for example, suppose I want to heat up argon by 1 degree Kelvin. And let's say I have 1 mole, okay? So to get the same situation for, let's say, water and, steam, right? If I wanted to heat up steam, 1 mole of steam by 1 degree of Kelvin, 2 times the energy must be supplied for the water than for the argon because of the degrees of freedom, right? Because the nonlinear molecule has more degrees of freedom that heat has to be pumped into to actually get a temperature rise, okay? So now we're starting to learn about the secrets of the universe. And let's even keep going with this.